Hello, calculus students. Today we're going to start looking at a little bit more complex integration. And the key to most integration problems that go beyond just the factual integrals you should just be able to say the answer to immediately pretty much, is there's some kind of substitution or other fancier manipulation involved. So this year in Calc 1 we're going to be mainly focused around substitution with what's called a U-substitution. So that's just one particular type of integration, but it's the most common or the most ubiquitous integral that you run into, and it comes up in other techniques as well. So next year we'll look at a few more different types of substitution like trigonometric and integration by parts and so forth. So this one's kind of the root of all of those. Now there are different ways to think about these problems. Some of these you can also do in your head. It depends how good you are at the chain rules. So if you're like my wife in high school, she always liked to use the Zen method. I'll use my teacher's name for it, which is stare at problem, think about all of the complications due to the chain rule, and write down the answer. I don't care if you use the Zen method. It's wonderful for easier problems. But if you get the answer wrong, then it's wrong, and you better be able to do it with a more show your work kind of method, which is what U-sub is. So U-sub should be something you fall back on. Just another quick story, just for you Zenners, because I know there's going to be some of you. My brother's calculus class in high school, he was the same age as many of you. I think he was in BC Calc as a sophomore. Took the same class as a sophomore. Well, he's a little ahead. So he was in BC Calc as a sophomore, just like Katie, Sam, and Gabe were. And he was not the best mathematical student in some ways. If this gets out on YouTube, oh, I'm sorry. But he was very determined. So he sometimes couldn't do the Zen method, but he was very good at writing out his substitutions, and he could do almost all integrals pretty much perfectly with substitutions because I told him to focus on it that way. A lot of his friends who were better at math maybe thought that they were hot stuff and would always try to be like, answer, Zen method. And once they got to harder problems, they were like, and then they'd be like, answer? And it'd be kind of right and kind of wrong. And my brother just sit there and be like, yep, it's this. So don't be too arrogant. Get the right answer. That's what I'm saying to you, okay? So enough fun times for this video. The purpose of U-substitution is to compensate for the chain rule. And the chain rule sometimes can be easy to compensate for, so you can Zen it, and sometimes it's a little tougher to compensate for. So in general, we're going to think about searching for an inside and an outside function. So they're not going to look like this, right? They're going to look like different specific functions. But think about it theoretically as you're integrating something that involves a chain rule. In other words, you have a composition. And if you're going to do it Zen or U-substitution, you want to be thinking about inside and outside. So here the outside is clearly right here. That's going to be a derivative. So I'm searching for an outside derivative, and then there's an inside right here. And I've got to have both of those components if I'm thinking like this, whether I do it with Zen or whether I do it by writing stuff down formally. Okay? So, really key to think like that. Let's start looking at some problems. So, do we see a convenient inside, and do we see the derivative of that inside lurking outside here? What's the inside? X cubed plus 1. So if we're doing this formally, we're going to say that is U. And is there the derivative of that thing lurking around somewhere outside? Right there, right? So that is du. But you don't want to think about it as exactly like that. If you've identified what you think is the inside, sometimes you're not going to be sure. This one's super easy to see. Sometimes you're not going to be sure. Guess. Think, well, maybe this is what U should be. Maybe this is the inside. Then just look at that and do the differential. Take the derivative. So what's the derivative of that? Forget about this.
3x squared.
3x squared plus 0, right? It's really du dx. I like to do this thinking about it as a differential, so it's du equals that dx. Or if you just want to take the derivative and multiply, that's fine too. Either way you want to think about it. Okay, cool. Then you substitute. That's why it's called a U-substitution. So you say that is equivalent to this part and this part together make what? This is a key. Think of it as like the key to a map, so you can find your treasure. Those parts together make what? Du. You can put it at the end because that's usually where dx and d stuff goes in an integral, right? We've seen that enough. And then what else do we have left? Can you guys help me? This stuff is u, and you've also got a square root. Okay? There you go. You've changed something in terms of x into something in terms totally of u. So now you just do the easy problem. This is one we should know how to do. I think of it like this, right? So then I go, that's u to the 3/2, 2/3, plus a constant. But then, of course, the problem didn't ask me about this weird u thing that I artificially introduced. The problem asked me about that x stuff. So you go to your map and say, oh, u is actually that x stuff. You should be doing this very concretely, and it won't be mysterious. It shouldn't be mysterious. If it's mysterious, you're trying to do Zen, and just stop it, okay? So we've got 2/3 u to the 3/2 plus c. That is the answer. All right. Let's do another one. I can see some people are clicking, some people are not yet. Do we see what we might think of as an inside? Remember, you might not guess it right on the first one. This one's a pretty easy again, though, I think. There's a clear inside. It's probably tangent x plus 3. Let's see if that works. So we're thinking, well, in this case, I want to make u tangent of x plus 3. Is the derivative of tangent of x plus 3 lurking around outside? That's how you decide on the harder problems. Right now, it's like, well, duh. Tangent of x plus 3, what's its derivative? Forget about it. Secant squared plus nothing. So then you're like, huh, did it work? You're going to find out if it worked right now. So you're like, well, that is u squared, and these parts together make du. And that's a super easy integral, so the answer is translated, the answer is
the tangent plus 3 cubed over 3 plus.
very nice. Mr. Parker? There we go. Let's do another. I think we need several examples today. Once you get this, though, man, it is a powerful technique. So, on this one, erase this guy, erase this as well, kind of clear us up. So we'll do number 3, which is lurking around down there. So, any suggestions on this guy, what my u should be? It's not rocket science here, right? There's not a lot of choices. We're going to get to problems where it's like, the inside might be this part, the inside might be this part. You just have to try a few things and see if it works out. If it doesn't work out, you'll know. It shouldn't be mysterious. We'll see where that happens on another one. This one, though, I don't think there's a lot of insides. If the inside is not x to the 4th, like it's pretty hard to guess what it would be. Maybe sine x to the 4th, exactly. Good. Let's just try this one, though. So if u is that, then du is what? Don't forget your notation. This is not only notation, this is the key to why this concept works and starts to matter more and more the higher you go. So we use it a lot, the notation next year. So that means that this integral is exactly equivalent to what? We've got the... yes, I heard it. 3 du. Very nice. That's good. You guys are thinking a little abstractly there. So I'm going to show you mechanically how to think about it. But it's sine of u at least, right? And I agree, 3 du does go here. Let's make sure that we're real clear about this for harder problems, though. If you weren't sure, like if that 12 is not exactly that 4, If they don't quite match, that's okay. You can just solve for what you have. You can be like, well, dx is du over 4x cubed, right? If you wanted to. So then you could just like substitute. That's what I want you thinking, like grab, put. So dx, I could put du over 4x cubed. Now at this point you should be like, well, something's wrong because there's x's and u's, and if that's what you're thinking, you're correct, your instinct is correct. But see, you can think about it as like this part's still there, right? So they cancel out, and what do you have left? 12 over 4 is 3 sine of u du. You guys who saw that that was 3 du's though, bravo, you're already really getting it. Okay, so what is the answer to that? That's an easy integral. 3 comes outside, right? Integral sign is? Negative cosine of u. So the answer is negative 3 cosine of x to the 4th plus c. Once you get real good at this, this is a totally Zenable problem. Like I would do this with Zen. These guys probably almost all would do this with Zen. They're just going to be like, I see a thing. I see derivative of inside of that thing out here. It's like almost totally out there. I'm just missing the 3. So this is really integral of 3 of the thing, which is that. But even that might be a little dangerous once you get pretty good at this. So learn the substitution and nothing will be mysterious. Let's do a few more problems. Let's do this guy. This guy. We'll wrap up with this guy. So if you're watching the video right now, you might try these first 2 problems at least, pause it, and then see if you get it right. Alright, so you should have tried at least 1 or 2 of these. So in this one, I think the obvious, it's still pretty obvious on this problem that the inside is secant. Now that might not work, of course, but in this particular integral it does, because if you take the derivative of secant is a factual thing we should know. Secant tangent. And voila! It's lurking right there. You see it? It's like outside spying. So it's totally right there. So you could even think about this 8 being moved outside if you don't want to, right? You can totally just move it outside. This part with that part is dz. No. That's du. And we've got the cube root of u, which is in other words u to the 1/3. So this is 8 u to the what?
It's 2
4/3, 3/4 plus c. Change it into the right thing, and you're done. 8 over 4 is 2, 6 secant to the 4/3 plus c. If you want to write that like this, great. Okay, so there's another one that I think is pretty easy. Those are all what I would call easy level problems. Let's see if this next one is the same kind of way. So I'm going to go a little bit quicker now. So here, u is x squared plus 1. That's the obvious inside. Does it work? If you're looking at that and going like, well, I don't have a 2.
divided by 2.
Just go like this in your key, and you have that right there. So this is, or you can think of it other ways too, but I think that's a great way to think of it, which will help us with this little bit harder one next. So that means that this stuff is what? It is du over 2, or 1/2 du. Yes, this stuff is
Root u.
u to the 1/2, or root u. So that means that that's 1/2 times this integral. So that's going to be u to the 3/2, 2/3. Good. Really, I should have put it here too, right? I might hold you slightly past the bell, so just be aware. So there we go on that one. Let's look at this guy. So this guy, what would your choice for u be?
At 2x minus 1, but then it gets moved.
Okay, so you're like, that's my choice. du is
2.
2 dx. So then you're like, okay, I'm converting. So I've got the square root of u. dx is du over 2 if you divide to that side, right? And then you're like, but so in most cases at that point you should be like, well, I'm going to scrap this and try a different u.
There is no other u.
There isn't really any other choice here. I mean, you could, I guess, try this, but it's going to get more complicated and not necessarily work either. So this is one where you're going to need to manipulate the key a little bit further.
Should you add an x to time?
I need what x is. Do I have somewhere that tells me what x is?
Yeah, u.
Could I get it from here?
Yeah, u plus 1 divided by 2.
Manipulate the key. Add 1 to both sides, and then divide by 2. And that says what x is. So go back to your key and use it again. And instead of x, I can put u plus 1 over 2. Now you might look at that and be like, well, this one's just as yucky as that one was, but I don't think it's true. Here you can't do anything to simplify. Like x times square root of stuff is x times square root of stuff. I guess you could put the x inside. That's not going to help. You can make it x squared inside, but that's not going to work. Whereas here you definitely have something that you can just distribute.
U plus 1.
1/2 times 1/2 is 1/4. That's outside.
Can that be a new measure?
That can be distributed.
Yeah, because then you have u plus 1 is actually...
What's u times root u? 1/2. That's u to the 3/2. I'm still in my integral, right?
Can't you simplify that first?
So you gotta do it this way.
Did that one first get rid back yet?
I don't know why I would do that. You could, right? But that was not intentional. Very good. So this is going to be u to the 3/2 when you distribute there, plus u to the 1/2 or root u. And then both of those are just separate pieces, which you can do easily. So I don't need my integral anymore. Antiderivative here is
5/2 2/5 times 2u to the 3. Wait, no, just kidding.
you can either put parentheses or distribute. I distributed
2/3 u to the 3/2 plus c.
We okay? Questions? So simplify. I think that's 2 over 20, which is 1/10. U is 2x minus 1 to the 5/2 plus 1/6 u to the 3/2. There we go. What's the only thing I really haven't shown you today yet? These are all what kind of integrals that I've shown you so far?
Indefinite.
Yeah, very nice. They're indefinite because they don't have
They have a c.
they have a c. They don't have an interval, right? Where you actually get an area under the curve. So let's do one of those real quick before we leave today.
That's a cycle.
So let's integrate. Let's see what I have. From, I don't know, this is not very good. Let's go from -3 to 6 of 5x times x squared minus 3 cubed dx. For our last one. Now you can do this a couple different ways, so I'll show you one other way tomorrow with the last example. But the way that I'm going to do this is I'm just going to pretend these aren't here at the beginning. I'm going to figure out what the antiderivative is, and then I'm going to put them back in. Okay, I think that's the easiest way to do it, which I'd recommend using most of the time.
So U is
Okay, so I'm just going to be like, pretending they're gone.
Your U is x squared minus 3. So your du is 2x. And then that's
Put the 5 outside, right?
yeah. So 5.
1/2 times U cubed.
That is that. Then I've got this, which is that. Am I missing anything?
1/2
Now
I substituted it
now we can
directly.
change it
You're right,
to
though.
U cubed over 2.
Integrate now, antiderivative. So if I don't want that plus c, then what I can do is just say not equal to, but now I can put the integral from -3 to 6 of this is actually equal to Okay, so that's the way to avoid worrying about notation. Notice, this is kind of floating, right? It's not equal to anything. So that's just really a technicality, but that technicality turns out to matter sometimes. So I'll show you another way to do that. Another approach basically that we'll look at tomorrow is instead of thinking about these both, they were really x right here. You guys know what I mean? Everything is x. You've got to use your key and turn them into u as well, which is another approach. I don't like it as much, I just like ignoring the problem. Doing it at the end. Yeah, so I'll show you one like that tomorrow. It's no biggie. So let's get the final answer here though. 5/8 times, what's that gonna be?
They were really late.
Oh gosh, that was a big
Let's not do it.
Times 5/8.
See you next time.
I agree.